Many people want to enjoy the now as time is limited. However, one thing that might confound them is the theory that in time, the past may not even exist. How so? What do scientists say about the past existing or not? And what happens to all the beautiful memories you've created if the past doesn't exist? Keep watching as we dive into the issue of whether the past exists. The debate about time has been, pardon the pun, timeless. Philosophers of old also wondered about what time really was, so if you find yourself wondering the same thing, have no fear, you are not losing your mind. If you want to know what time it is, you look at your wristwatch. The watch can be synchronized with your phone, which syncs to the network that syncs with the atomic clock. The time value you finally see is accurate enough not to be off by more than a second over 1 million human lifetimes. And it's worth noting that the rotation of the Earth around its axis and its revolution around the Sun is no longer accurate enough to be used as timekeeping standards. Understanding the flow of time began with understanding correlations between observable natural periodicities. What has been seen and measured throughout human history has shaped the time theories proposed by contemporary thinkers, philosophers, and scientists. The first farmers over 10,000 years ago, by the way, used constellation periodicity to predict seasons and scheduled nighttime work for full moon nights. Around 1500 BC, our ancestors were inspired to build sundials and water clocks in order to be more granular in modeling natural periodicity. The ubiquitous circular face of modern analog clocks is derived from sundials. In Vedic texts dating to the 2nd millennium BC, Indian philosophers profess that the universe goes through repeated cycles of creation, destruction, and rebirth through Kal Chakra, or the Wheel of Time. And this was not our history's only reference to a cyclical concept of time. Plato, who lived in the 4th century BC, believed that we're a part of a large time machine and that when planetary configurations return to their initial state, a process that takes 25,800 years, everything would restart. So if you found yourself at the tail end of the cycle, make sure to quickly wrap up your affairs before the grand reboot. But actually, this concept has modern scientific support as well. According to a group of modern cosmologists, the universe has a bouncy fate, meaning it will go through repeated cycles of expansion and contraction. We are currently in an accelerated expansion phase. Aristotle, Plato's student, however, had a different perspective on time. Time, he saw, was an attribute of motion, a measure of change. To him, time does not exist in and of itself. He called time the enumeration of continuous movement, or the number of changes in respect of before and after. He contended that because time is essentially a measure of change, it necessitates the presence of a soul capable of numbering the movement. He also called the realness of time into question. One of the major turning points in our understanding of time can be attributed to the Italian physicist and mathematician Galileo Galilei. He began working with time after noticing the swinging of the bronze chandelier in Pisa Cathedral and comparing its periodic motion to the regular beat of his own pulse one day. Galileo noticed that contrary to popular belief, the number of beats required by the chandelier to complete a swing did not decrease as the lantern's motion decreased but remained nearly constant. This was a significant discovery that influenced the science of time flow from that point forward. Using Galileo's discovery, Dutch inventor Huygens created pendulum-driven clocks in the late 17th century, which became accurate enough that minute hands were added to the clock face. For a long time, until 1927, the pendulum clock was the most accurate timekeeper. However, the pendulum clock had its limit. Marine chronometers were created because pendulum clocks could not be used for navigation on the decks of rocking ships. These portable, precise timepieces aided in hastening the age of discovery and colonialism. Around the same time, Newton famously witnessed the apple fall. The scholium at the beginning of Principia best describes his perspective on time. He came to the conclusion that absolute time is measurable but imperceptible, and that it can only be truly comprehended mathematically. For him, one-dimensional absolute time and three-dimensional geometry of the universe were independent and separate aspects of objective reality, and all events in the universe occurred simultaneously at any given point in absolute time. However, Albert Einstein came around and introduced a new concept about a topic we thought we knew so well. Yes, you knew we would mention him, right? Einstein has a way of popping up on this kind of topic. Einstein overturned the concept of simultaneity in the early 20th century with his theory of special relativity. According to the theory of relativity, simultaneity is not an absolute relationship between events. What is simultaneous in one frame of reference may not be simultaneous in another. According to Einstein, the universe has no single timekeeper. When something happens depends on one's precise location in relation to what one is observing. Consider the following scenario. Imagine one observer seated in the middle of a speeding train car and another standing on a platform as the train passes. Just as the two observers pass each other, a flash of light appears in the center of the train car. According to the train observer, the front and back of the train car are at fixed distances from the light source, and the light will reach the front and back of the train car at the same time. For the observer waiting on the platform, the back of the train car is moving or catching up toward the location of the flash, while the front of the train car is moving away from it. Because the speed of light is finite and constant in all directions for all observers, the light traveling to the back of the train will travel less distance than the light traveling to the front. As a result, the light flashes will strike the train car's ends at different times, according to the observer waiting on the platform. What appeared to be a simultaneous flash to the observer inside the train car was not a simultaneous event to the observer outside. The difference in observed time between observers moving at different speeds is known as time dilation. Although it may appear counter to common sense, time dilation has been experimentally validated by precise measurements of atomic clocks flown in aircraft and satellites. This theory both conceptually and practically allows for, wait for it, time travel into the future. Going really fast allows one to travel to the future at a rate faster than 1 hour per hour. However, for us to notice this time travel, the speed must be very high, close to the speed of light. Here is a practical case of time dilation. A cosmic ray muon is an unstable subatomic particle with a mean lifetime of 2.2 microseconds. Because of this short mean lifetime, you would expect cosmic ray muons to travel only 660 meters before decaying, assuming light speed equals 300,000 kilometers per second. The effects of time dilation allow them to survive the over 100-kilometer-long flight to Earth's surface and beyond, and because of their high velocity, muons have a longer half-life in the Earth's reference frame. As a result, roughly 1 muon passes through your palm every second. However, one of Einstein's former professors, Hermann Minkowski, came up with the idea of space-time, a four-dimensional continuum that lumps space and time into a single formulation. Space-time acts as a platform for particles to move through the universe in relation to one another. When particles are in the same space-time location, they can interact. However, this version of space-time was lacking. It did not include gravity until Einstein's general theory of relativity was published in 1916. The fabric of space-time is continuous and smooth, but it is curved and deformed when matter and energy are present. According to the theory, what we perceive as gravity is the warping of space and time. Gravity is the curvature of the universe caused by massive bodies and other forms of energy, and it determines the path that objects travel along. The curvature is dynamic, shifting as the objects do. Physicist John Wheeler came up with this conundrum about the relationship between space-time and mass, the physical concept that you can see. He said, space-time grips mass, telling it how to move. Mass grips space-time, telling it how to curve. Minkowski's theory also explains how gravitational fields can slow the passage of time for an object seen from outside the field. For example, to keep their clocks synchronized with the ones on Earth, GPS satellites use both special and general relativity. The satellite sends a time signal to a GPS receiver, which measures the time it takes for the signal to reach the receiver to determine its distance from the satellite. Even minor misalignments would accumulate over time to cause significant errors in on-ground navigation. Both the satellite's orbital speed and the difference in space-time curvature between the satellite in orbit and the receiver on Earth's surface must be considered to obtain an accurate positioning system. Now, if we extrapolate and imagine places of extreme gravity such as a black hole, an object falling into one appears to slow as it approaches the event horizon, taking an infinite time to reach it. The object appears to be eternally stuck at the event horizon to an observer outside the event horizon. Time appears to pass normally for the observer who falls in, though from his vantage point, it would only take him seconds to reach the singularity at the heart of even the most massive black holes. And there could also be potential space-time distortions that would allow time machines to function. There is the concept of wormholes, which can be imagined as space-time shortcuts. When two causally disconnected regions are linked, it is possible to link not only two different locations in the universe, but also two different locations in time. Traveling back in time might be possible if such a wormhole could be found. But although the theory is sound, we have yet to see evidence of a wormhole in our universe. Our methods and implements for measuring time have improved over time. The second, the International Standard Time Unit, has had its definition evolve from a fraction of a solar day to a fraction of an ephemeris year to the atomic second in the modern quantum era. Since 1967, the second has been defined as 9,192,631,770 times the period of the radiation corresponding to the transition between the two hyperfine levels of the cesium-133 atom's ground state. In understanding time, our tools supplement our flights of imagination. We have increasingly viewed time through the quantum lens over the last century. And there you have it. Quantum mechanics has entered the discussion. However, there is a difference in how quantum mechanics and general relativity approach the flow of time. The former considers it as universal and absolute in a selected rest frame, while the latter regards the flow of time as malleable and relative. The Wheeler-DeWitt equation was born from the seemingly impossible combination of quantum mechanics and general relativity. This equation solved one problem while creating a new one. In this equation, time plays no role. This led to a big conundrum among physicists, which is referred to as the problem of time. So is this to say that time has no meaning in the fundamental laws of nature? Well, there is a way to look at this impossible situation. We never truly see time, right? We only see clocks. When you say this object moves, you really mean that it is present when the hand of your clock is present, and so on. We say we measure time with clocks, but we only see the hands, not the time itself. And the hands of a clock, like any other physical variable, are a physical variable. In some ways, we cheat because what we really observe are physical variables as a function of other physical variables, but we represent that as if everything is evolving in time. With the Wheeler-DeWitt equation, we get the opportunity of stopping to play the game of unseen variables. Instead of introducing a fictitious variable, that is time, which is not observable in and of itself, we should simply describe how the variables are related to one another. So is time a fundamental property of reality, or merely the macroscopic appearance of things? It is only a macroscopic effect. It only appears for significant events. However, is debating whether time exists not rather counterproductive? Shouldn't the question of whether the time is emergent or fundamental be more worthy of scientific investigation? Temperature and pressure remained real after we recognized them as emergent properties of an underlying atomic description. Well, while this is the most pressing open question about time, it is far from the only one. There is another puzzle that confounded many a wise man concerning time. Time always points to the future, which all the laws of physics cannot explain. The fact is that all fundamental laws, whether Newton's, Einstein's, or quantum rules, would function equally well if time were reversed. However, the opposite is the most common perception of the world, in that time moves in a specific direction. We are born, age, and die. Eggs break, liquids mix, and our offices tend to become more disorganized, strictly not the other way around. As far as we can tell, time is a one-way street. It never reverses, despite the fact that no laws prevent it from doing so. This one-way behavior is inherent in only one scientific law, the second law of thermodynamics, which states that the entropy of isolated systems tends to increase rather than decrease over time. The second law implies that time is asymmetrical with respect to the amount of order in an isolated system. As a system advances through time, it becomes more statistically disordered. When an ice cube is dropped into a hot cup of coffee, it both cools the coffee and heats the ice cube. The process, however, is irreversible. It is a one-way street. But the law says nothing about why this happens. Lowering entropy would be equivalent to reversing time's arrow. In a 19th century thought experiment, a powerful imp known as Maxwell's demon can perform such a separation for gas by knowing the position and speed of every gas molecule in a box with a partition. The demon uses a shutter over a hole in the partition to restrict high-energy molecules to one side while allowing low-energy molecules to collect on the other. However, the demon would have to expend energy and raise its own entropy, so the total entropy of the universe would still rise. And yet, a recent experiment claims to have been able to replicate Maxwell's demon for approximately 60 atoms, lowering the system's entropy by 2.44. This has enormous potential in the world of quantum computing. If Maxwell's demon could be replicated at a classical scale, one could argue that time reversal would be thermodynamically feasible. However, this might not result in us experiencing yesterday again because it relates to a different notion of time, the perceptive arrow of time, which lines up perfectly with humanity's psychological perception of time. Things that we remember stay in the past. We know we've progressed in time when we can remember more things now than we could in a previous moment. We appear to be capable of recalling whether or not we knew something in the past. We appear to be able to predict future events with varying degrees of accuracy, but we also lack complete knowledge of the future. The psychological flow of time is inextricably linked to human memory and our understanding of cause and effect, and it is heavily influenced by dopamine levels, and time perception impairment has been observed in subjects with dopamine-related impairments such as Parkinson's disease, schizophrenia, and attention deficit hyperactivity disorder, or ADHD. The relationship between the thermodynamic arrow and the perceptive arrow of time is not well established in physics, but there are several theories that could provide a solution. For example, the Copenhagen interpretation of quantum mechanics says quantum evolution is governed by the time-symmetric Schrödinger equation, and irreversibility in the quantum arrow of time results from wave function collapse. When entropy changes, information flows rather than heat in the quantum mechanical version of entropy. Some quantum physicists claim to have discovered the fundamental source of the time arrow. They claim that energy disperses and objects equilibrate as a result of the way elementary particles become intertwined when they interact, a strange effect known as quantum entanglement. Einstein and his colleagues first proposed the concept of quantum entanglement as a mental experiment. They discovered quantum entanglement lurking in quantum mechanics equations and realized its utter strangeness. Quantum entanglement describes particles that are mysteriously linked no matter how far apart they are. Einstein thought such behavior was impossible because it contradicted the local realist view of causality. How could particles located far apart influence each other instantly? They contended that the accepted formulation of quantum mechanics was, therefore, insufficient. However, an Irish physicist named John Stuart Bell devised an experimental test that disproved Einstein's theory that there could be a predetermined understanding between particles. As a result, the widely held belief is that information does indeed travel between entangled particles, potentially at speeds faster than light. Entangled particles, if separated by light years, could theoretically share information instantly. Not only can two events be correlated, linking the earlier one to the later one, but two events can become so correlated that it's impossible to tell which is which. To the best of our knowledge, entangled particles do not appear to have time. If you have space-time, you have a well-defined causal order. However, if there is no well-defined causal order, there is no space-time. Some physicists interpret this as evidence for a profoundly counterintuitive worldview in which quantum correlations are more fundamental than space-time, and space-time itself is built up from correlations between events. However, there is another theory about time out there that seeks to explain the universe as a giant block. Unsurprisingly, this theory is known as the block universe or block time theory. According to the block universe theory, the universe is a massive block of everything that ever happens at any time or place. According to this viewpoint, the past, present, and future all exist and are all equally real. The block has 4 dimensions, 3 spatial dimensions, length, height, and width, and 1 temporal dimension, time. You can get this concept by visualizing the world's block model as a 3-dimensional rectangle or cuboid. 2 of the dimensions of that cuboid, say height and width, represent 2 of the universe's 3 spatial dimensions. The length of the cuboid is replaced with time. The Big Bang is located at one end of the cuboid. At the other end of the spectrum is the universe's final moments. Every event that has ever occurred is represented by a cuboid. The location of these events in the cuboid represents their location in space-time. The block contains all events, including your birth and death, as well as this very moment that you hear these words. In the block universe, time doesn't pass, meaning there is no specific present moment in a block universe, and past and future moments are relative. Consider the concept of here. I've arrived. While hearing this, you can truly say, I am here, even if your here differs from others. Talking about the present or now works the same way as talking about here on the block universe model. Remember perhaps last week when you said to your late arriving friend for coffee, now you're here, or when Caesar said, I am now crossing the Rubicon. Both of these assertions are correct. That is because talking about the present or now simply refers to the point in time where you happen to be. Everyone is in the present just as everyone is in the place they call here, because we are always located wherever we are, which is trivially true. Time or temporal relations of earlier than and later than exist according to the block universe view. These bonds exist regardless of where anyone is. Let's see if this video has been able to change your view of time in the comments section below.